Hey everyone, welcome back to Chem Story. In today's lesson, we're diving into another important reaction intermediate in organic chemistry, carbon radicals. These little guys show up all over the place in organic reactions. And if you really want to get good at reaction mechanisms, you've got to understand how carbon radicals work, their structure, their stability, and how they behave. So let's walk through it together step by step and break it all down in a way that makes sense. So what exactly is a carbon radical? It's a reaction intermediate where a carbon atom has just 3 bonds and 1 unpaired electron. Now, most carbon atoms are tetravalent, meaning they usually make 4 bonds to fill their octet. But in a radical, that carbon only has 7 valence electrons, so it's electron deficient. But here's the interesting part. It's still electrically neutral. There's no formal charge on it. Even though it's short 1 electron, it doesn't carry a positive or negative charge. Because it's missing a full octet, it's super reactive, always looking for another unpaired electron to pair with. That's what makes carbon radicals so useful in chemistry. There are 2 main ways we can classify carbon radicals. One is based on hybridization, and the other is based on how many groups are attached to the radical carbon. Let's start with hybridization. Unlike carbocation ions, which are always sp2 hybridized and have a flat trigonal shape, carbon radicals are a little more flexible. They usually have a shallow pyramidal shape, kind of in between sp3 and sp2. In fact, in many cases, they look almost flat like an sp2 carbon, but they're constantly flipping between 2 pyramidal forms because the energy barrier is so low. That's why we often say radicals are nearly sp2 hybridized, even though they still hold on to a bit of sp3 character. Now, this geometry actually depends a lot on both steric and electronic factors. Primary radicals, which have fewer bulky groups around them, tend to be more pyramidal, but tertiary radicals with more substituents are more stabilized and end up looking flatter, more like a true sp2 carbon. This flexibility in shape plays a big role in how stable and reactive a radical is. Another way we classify radicals is by looking at how many alkyl groups are attached. Just like with carbocation ions, we call them methyl, primary, secondary, or tertiary, based on whether there are 0, 1, 2, or 3 alkyl groups attached. Alright, now let's take a closer look at the structure so this makes more sense. If you check out the diagram, you'll see different types of alkyl radicals, from tertiary all the way down to methyl. Unlike carbocation ions, which have an empty p orbital, radicals have an unpaired electron sitting in that same spot. So it's not empty anymore, just half filled. That makes them super reactive. And here's something important. The number of alkyl groups really affects stability. Tertiary radicals with 3 alkyl groups are the most stable. Methyl radicals with none are the least stable. Now let's take a look at vinyl radicals. These are a bit different from the alkyl radicals we just saw. In a vinyl radical, the radical carbon is directly attached to a double bond, so it's sp hybridized. That gives it a linear geometry, with the unpaired electron sitting in a p orbital that's perpendicular to the pi bond. Because of that setup, vinyl radicals don't have the same flexibility as alkyl radicals. Their structure is more rigid. They can't flip or bend the way alkyl radicals can. That's all we need to know about their structure for now. So what actually makes a carbon radical more or less stable? Even though they're electrically neutral, meaning there's no formal charge, carbon radicals are still considered electron deficient. Why? Because they only have 7 valence electrons, not a full octet. And that missing electron makes them highly reactive. But not all radicals are equally unstable. And there are a few key factors that help stabilize them. Alright, let's break down the main factors that affect radical stability. First, we've got alkyl substitution. The more alkyl groups attached to the radical carbon, the more stable it becomes. That's because alkyl groups help spread out the electron deficiency through something called hyperconjugation and also inductive effects. That's why tertiary radicals with 3 alkyl groups are more stable than secondary or primary ones. Next is resonance stabilization. If a radical can form resonance structures, in other words, if the unpaired electron can spread out over multiple atoms, it becomes way more stable. That's what makes allylic and benzylic radicals so much more stable than regular alkyl radicals. They can share that unpaired electron across a larger system, which lowers their reactivity. And finally, bond strength. If the bond that breaks to form the radical is weak, then it's easier to make that radical. And the radical itself tends to be more stable. Because it takes less energy to break that bond, the radical is less likely to fall apart and go back to where it started. You can actually see this trend really clearly if you look at bond dissociation energy, or BDE. As the number of alkyl groups increases, the energy needed to break a CH bond goes down. In other words, more substituted alkanes form radicals more easily. Here's how the numbers stack up. Forming a methyl radical takes about 435 kilojoules per mole. A primary radical needs around 410, secondary is about 397, and tertiary just 381. So tertiary radicals are not only more stable, they're also the easiest to make. This shows just how closely radical stability is tied to bond strength. The weaker the bond, the easier it is to form a radical and the more likely it is to stick around and react. Since BDE plays such a big role in radical formation, the next step is to see how these radicals actually behave in real reactions. Let's check out a few key examples. Radicals might be short-lived, but they're involved in some really important organic reactions. A classic example is alkane halogenation, where a hydrogen atom gets swapped out for a halogen, like chlorine or bromine. And the whole thing runs through a radical chain mechanism. That means it goes through three main steps: initiation, propagation, and termination. This reaction is super useful because it lets you add halogens to simple hydrocarbons, and that makes them way more reactive for later transformations. Here's another important one: the addition of HBr to alkenes or alkynes, but this time in the presence of peroxides. What's interesting here is that the reaction doesn't follow Markovnikov's rule like it usually does. Instead, because it starts with a radical initiator, the peroxide, the reaction goes the other way, giving you anti-Markovnikov products. It still follows a radical chain mechanism. The peroxide kicks things off by forming a bromine radical, which then adds to the double or triple bond, creating a new carbon radical, and the chain keeps going from there. And here's one more example: dissolving metal reduction of alkynes to transalkenes. This one uses sodium metal and liquid ammonia, or Na over NH3, to generate radical anions. Then those anions get protonated and go through a couple more electron transfers, eventually giving you a highly selective transalkene. This method is especially useful when you want to reduce alkynes in a stereoselective way, and it's a go-to trick in organic synthesis. So overall, these reactions really show how versatile carbon radicals are. Once you understand how they form and react, you can start controlling reaction pathways, and that means more efficient and selective transformations in the lab. Alright, that's it for today's lesson. I hope this helped make carbon radicals a little clearer. If you enjoyed the video, don't forget to like, subscribe, and hit the bell so you don't miss the next one. Thanks for watching, and I'll see you in the next one.